Okay, so I'm Veroshin, and this is my EECS 370 video. I'm going to be talking about caches today. So first, caches are pretty much just a more efficient way of dealing with memory. Regular DRAM that we usually use for main memory really takes a lot of cycles, even though it's cheap. SRAM, on the other hand, is a bit more expensive, but it's also a lot faster. So what we can do is when we use certain memory locations, we can bring them into the cache and make references to these locations a lot faster. So we're going to talk about a block size of 2. Which basically means in any cache location, you're really going to store the data from 2 different addresses that are right next to each other. So we're going to use these memory references 0 to 11, 3, 4, 7, 12. First, we're going to talk about fully associative cache. Don't worry about what that means yet. So first, let's bring in the data from memory location 0 to the cache. Okay, we're not going to actually talk about the data. We'll just talk about the indices. So we want to bring 0 into the cache in our fully associative table over here. So what we're going to do is we're going to put both 0 and 1 here. Okay. So now if we reference this later, it's going to be a lot faster. You know, to pull the 0 and 1 from main memory would have taken a lot more cycles because we would have used DRAM. But now we're going to use SRAM if we reference this again. So now let's access memory location 2. We're going to bring in memory locations 2 and 3 because our block size is 2 again. Okay, so from these 2 memory locations that we've brought in, you can tell that it's initially an even address and then an odd address. Okay, so what do we do when we bring in address 11? Well, looking at the binary, right, the last bit is set to a 1. We want is to start at a address that ends in a 0, which is going to be 10 because you just subtract 1. So what we're going to do is we're going to load in 10 and 11. Okay, and this is, you know, that block size of 2 again. So now we're going to access 3. We're going to look through our cache and we see that 3 is already in here. So we don't even need to bring it from the main memory again. It's a lot quicker because it's already in the cache. So there's going to be a cache hit. Okay, now we're going to load in memory address 4. It's even, so we can just do 4 and 5. Okay, now our cache is full. So if we want to pull something in now, that's now already in here. We have to basically make room for it. So now we want memory address 7. Look through the cache, it's not here, right? So what we have to do is basically we have to find whatever we least recently used. Okay, that's a heuristic we use. And the thing we use the furthest back that we haven't used recently is this first entry, 0, 1. So what we're going to do is we are going to move this out and then replace it with 6, 7, because we want that even odd pair. Okay, now memory address 12, again, we don't have it. Well, we just loaded 6, 7 in. Right before that, we access 2, 3. So the least recent we use in this case is this 10, 11 block. So we're going to erase that now. And what we're going to put there now instead is going to be 12, 13, because we have that even odd pair. Okay, so that's fully associative. So fully associative just basically means any information can go anywhere in the cache. So to contrast that, what we're going to do is we're going to talk about direct map cache, which basically means any memory address can only be put into one location. And this can be a lot faster in terms of hardware. So we'll start off similar to how we did for fully associative. We'll load in 0 and 1. So 0, 1. And then we have 4 entries here. So the difference between fully associative and direct mapped is you can only load into one location. So how do we determine where we can load into? Well, in our memory addresses, like we said, we load in a even odd pair. So basically we can just look at that last bit of every address, right? Now, since we have 4 different locations or 4 different cache lines, we need 2 bits to encode that. So how can we do this? We can basically say the next 2 bits of the address. Whoops. Let's make that a bit neater. next two bits tell you where it's going to go into cache. So we did 0, 1, right? And this basically says 0, we'll put in index 0. Memory address 2, these 2 bits encode 0, 1, that's just regular 1. So we'll go to set index, we'll go to index 1 in the cache and put in 2 and 3 again. It's pretty much the same so far. So here is where it gets tricky. 11. This is going to turn to 10, right? Because we want to change this into a 0 and load that even odd pair. But this 11 maps to the same location as the 2. So what we have to do that we didn't do with a fully associative is we have to replace that 2-3 pair with a 10-11 pair. So let's do that here. Okay. And let's move on. Going to 3, this turns into a 0 bit, so your address becomes a 2. Well, unfortunately, we just got rid of it. And again, it maps to the same set. So once again, we're going to have to remove this. Replace it back with the 2-3 pair. Okay, so now we can move on to 4, 1, 0. Okay, that's binary for 3. Sorry, 2. So we're going to put it into index 2, 0, 1, 2. I'm going to put that 4, 5 pair. Now looking at 7, we want to put that even odd pair. So that becomes a 6. And then this entry number translates to 3. So we're going to put it in entry number 3, 0 indexed, of course. So we're going to do 6, 7 here. And then finally, with 12, we have that 1, 0 again. So that translates to 2, 0, 1, 2. That's going to replace the 4, 5 entry. So yeah, that was a pretty much quick introduction to fully associative and direct map caches. What we can talk about after this is, a kind of balance between the two called regular set associative. So clearly, these two different cache situations can be useful in different cases. And yeah.